It's my great pleasure to introduce Ilia Kofman from City University of New York. And the title is Mahler measure and the Vol-Det Conjecture.
Thank you very much. So let me start with a classical question in graph theory, and that is, how many spanning trees does a graph have? So essentially a complete answer was given by Kirchhoff in 1847 with the matrix tree theorem. So if you have a graph with, here's an example with 4 vertices, and these are its 3 spanning trees. So if you have an n vertices, then you construct the n by n Laplacian matrix, which is the diagonal matrix minus the adjacency matrix. On the diagonal, you put the degrees of the vertices, subtract off the adjacency matrix, and this is the Laplacian. And the matrix tree theorem is that the number of spanning trees is any cofactor of the Laplacian, which is 1 over n times the product of the non-zero eigenvalues. Okay, essentially a complete answer. But it's still surprisingly difficult to compute the number of spanning trees. So here is a 4 by 5 grid. So in general, the general formula for the m by n grid was only discovered by Temperley in 1974. Okay, so let me sort of test you guys. So here's a 4 by 5 grid. Think of a number. How many spanning trees does this graph have? I'll tell you in a moment, okay? So here's the construction. So this is Temperley's bijection. Start with the graph G. Take the planar dual G prime, G star, right? So this weird vertex is for the unbounded region. Overlay the 2 graphs, overlay G and G star. Subtract off 1 vertex of G and 1 vertex of G star. And what you get is a bipartite graph. So the bipartite graph has the black vertices are the vertices of G and the vertices of G star. And the white vertices are where the edges intersect. So this is a balanced bipartite graph where the number of black vertices and white vertices is the same. Okay? So what this allows you to do on a balanced bipartite graph is it allows you to compute the perfect matchings, what are called dimers. And I'll talk about that later in the talk. I'll give you a precise example and so on. But so everybody's got a number in their heads for what Temperley did is he was able to find a bijection. This is the bijection here, between the number of spanning trees of the graph, G, and the number of perfect matchings of the balanced bipartite graph. So here is the general formula for the number of spanning trees, and it turns out that 4 by 5 grid has more than 4 million spanning trees. 4,140,000 and some spanning trees. Sort of surprising, okay? But this is the general formula. And if you apply some number theory and basically treat this as a Riemann sum and then apply some analytic number theory, what you get is the spanning tree entropy, right? In this case, it's pi times the log of the number of spanning trees divided by the number of vertices. This is the spanning tree entropy as the number of vertices goes to infinity, so of the infinite square grid. And that number turns out to be 4c, where c is Catalan's constant. Okay? So this sort of 4c is also the volume of the hyperbolic regular ideal octahedron. And so the spanning tree entropy of the square grid is given by the volume of the hyperbolic regular ideal octahedron, a certain hyperbolic volume. And so this is the kind of prototypical example that I want to discuss, where we have a growth process, in this case the number of spanning trees, right? But in general it's some combinatorial or algebraic growth process where after applying some number theory, the exponential growth rate is given by a hyperbolic volume, right? And so this is the first example that I have here. Okay. So the next example is going to come from using the determinant. So the knot determinant was one of the first computable knot invariants. And by computable, I mean knot of the form minimize something over all knot diagrams, like the crossing number, the unknotting number, the bridge number, all of those kinds of things that are easy to define but hard to compute. So the determinant is...
computable has a technical definition, many technical definitions by computer scientists, and you may as well use them. So it's computable in polynomial time as opposed to other things which are
I agree completely.
Disastrously complicated.
Reason. So the determinant was defined as the determinant of the symmetrized Seifert matrix. Before that, it was actually known as the order of the first homology of the twofold branch cover of the knot. And more recently, it's now sort of, people usually think of it as the absolute value of the Jones polynomial at -1 or the Alexander polynomial at -1. And if it's an alternating knot or link, then you simply construct the Tate graph and count the number of spanning trees of the Tate graph. So for example, for the figure 8 knot, you take the checkerboard coloring. This is the associated Tate graph. It has 5 spanning trees, so the determinant of the figure 8 knot is 5. Okay.
Can I ask a question about the previous result?
On the previous slide. This
yes.
slide,
So
yes.
I remember there was a result of Lyon's where he proved that the growth of the number of spanning tree is more or less equal to the classically same determinant of the corresponding Laplacian. And is that
Can I address your question at the end of the talk?
Okay.
Okay. So that's it's related to this, but it's yeah. Okay. So this is the knot determinant. For an alternating diagram, basically the knot is equivalent up to mirror image from the diagram, right? So you can recover from the Tate graph, you take the medial construction and you get the diagram. From the diagram, you take the checkerboard coloring and you get the Tate graph. And so the two different checkerboard colorings give dual Tate graphs. Okay. So there's a connection between determinant and hyperbolic volume that was first noticed by Nathan Dunfield by doing when he was working on Snappy. And so here's one of his scatter plots of all 13 crossing alternating knots. And on one axis is volume, and on the other axis is the log of the determinant. And you can see some suggested relation here, sort of like asking for an explanation here. So in our work, what we sort of came across is a very simple relationship, that the volume is always less than 2 pi times the log of the knot determinant. And this is the Vol-Det Conjecture in the title.
If you go back a slide, what is the line that you're drawing?
Well, I don't know. It has some slope. Okay.
Okay. So how far is it from this cluster?
I don't know. So this is an inequality. This is an upper bound. Okay. So it's been verified. We verified it for all census knots. Stephen Burton verified it for 2 bridge links and alternating 3 braids. And what we showed is that 2 pi is sharp. And what that means is that if you take alpha less than 2 pi, then you can find infinitely many hyperbolic alternating knots such that alpha log determinant is less than vol. Okay. But here's another similarity, kind of a structural similarity. If you take a reduced alternating diagram and you let K prime be obtained by changing any proper subset of crossings, then the determinant drops. Okay? We conjectured that the volume also drops, and so we checked this. For the first 10 million alternating knots, we changed 1 crossing at a time, every single crossing, and without exception, the volume dropped. Sometimes to 0 if it was an unknotting operation. But this is open. This is an open conjecture. So somehow, in an alternating projection, you're maximizing both the determinant and the volume. So the number theory tool that we're going to use is Mahler measure. Okay? So the Mahler measure of a polynomial is defined to be this integral over the unit circle. And by Jensen's formula, it's just the sum of the logs of the roots that are outside the unit circle. So the one variable Mahler measure is sort of immediately obtained if you know the roots of the polynomial. For a 2 variable polynomial, the Mahler measure is defined by a very similar integral, now over the torus. But it's only known exactly for certain 2 variable polynomials, and for others it's an open research problem. Okay? There's no such nice formula. the two variable Mahler measures are related to hyperbolic volume because they can often be expressed using logarithms. Okay, so I'll talk about that also later. By the way, you can approximate a two variable Mahler measure numerically as much as you like. There are all kinds of theorems about approximations, but it's the exact computation that's open. So here's a comparison of sort of like how this volume in Mahler measure shows up. It's kind of fascinating. So the volume of the figure 8 knot is twice the volume of the regular ideal tetrahedron, 2v tet. Smith showed sort of as a remarkable discovery that opened, the door to this line of research, that 2 pi times the Mahler measure of 1 plus x plus y is related to a certain L function. And that's giving you the volume of the figure 8 knot. Boyd, following up on Smith's work, showed that pi times the Mahler measure of the A polynomial of the figure 8 knot is giving you the volume. And he showed this is true for many other A polynomials of one-cusp hyperbolic 3 manifolds, but not always. Okay, so this is one of those situations that happens often, but not always. And then Kenyon showed that 2 pi over 5 times the Mahler measure of this two-variable polynomial is giving you the volume of the figure 8 knot. This polynomial, we'll see later, comes out of the Dimer model. What's interesting is these two mathematicians were in the same university, at the university in Vancouver, UBC, working at the same time, coming up with these results, and they had no idea about each other's work. So what I want to talk about today, the sort of the primary thing I want to discuss, is biperiodic alternating links. Okay? So if L is an alternating link in R2 cross I, right, the projection graph G of L is a 4-valent biperiodic tiling of the Euclidean plane. Okay? So that's a biperiodic alternating link. Here are the two sort of primary examples. This is the infinite square weave, and its projection graph is the square lattice. And the triaxial link with its projection graph, which is the trihexagonal lattice. Okay? Now, the triaxial link appeared in a figure from Gauss's 1794 notebook, so it's clearly worth studying, but he may have been just doodling. There was no other math there about it. There are lots of examples of 4-valent semi-regular Euclidean tilings. There's a very nice Wikipedia page. And so all of these correspond to biperiodic alternating links, different ones. The semi-regular part is the fact that these are all regular polygons. So let's talk about the geometry, right? So if you take this is the infinite square weave. If you take the Z2 quotient, you get a link in the thickened torus, right? So this is the Z2 quotient of this. You get a link in the thickened torus. And so we want to think about T2 cross I minus W, right? So now the thickened torus itself is the complement of the Hopf link, where you take the cores of the Heegard tori, right? So that's a thickened torus, right? And so that means that this link in T2 cross I, right, the complement, this is also the complement, right? This is the complement of a link in S3 with a Hopf sublink. So these two components are the Hopf sublink. And you can feed that into Snappy and find the geometry, and it turns out that this has a complete hyperbolic structure with 4 regular ideal octahedra. Now, in general, so we want to talk about a biperiodic alternating link, and there it's invariant under some translations by a 2-dimensional lattice, such that toroidal quotient link is a link in T2 cross I with a toroidally alternating diagram on T2 cross 0. Okay? So what we proved is that if the projection graph is a semi-regular Euclidean tiling, right, then T2 cross I minus L is hyperbolic. It's a hyperbolic manifold. And it decomposes into regular ideal tetrahedra and octahedra with exactly this volume. The volume is 10A V tet plus B V oct, where A is the number of hexagons in the fundamental domain, and B is the number of squares in the fundamental domain. Okay? So in this example that we saw earlier, right, you can see that T2 cross I minus W has one regular ideal octahedron for each crossing. right? So this is one octahedron per crossing for the square weave. Okay, so now we need another idea, and this is this notion, a suitable notion of convergence for finite knots and links toward a biperiodic alternating link, right? So this is going to be called Fulner convergence almost everywhere, and this kind of convergence is a requirement to satisfy three conditions. So these are the three conditions. So these links contain increasing subsets, Gn of L, which eventually exhaust the biperiodic link. There's a Fulner condition that the limit, right, of the number of vertices in the boundary divided by the total number of vertices goes to 0. And you want these knots or links to not have too many other crossings. So you want the number of vertices in Gn divided by the number of crossings to go to 1. So here's a kind of a possible sequence.
So each Kn here is the link, right?
Yeah, so Kn is some finite link. And Gn is a subset of it. So like it's a chunk of square weave. So you can see like there's a big chunk of square weave in there. That's the Gn part, right? And so what you want is you want these Gn's to exhaust the square weave. You want bigger and bigger chunks of the square weave, for example. So this is this notion of a diagrammatic convergence of the finite links toward this biperiodic. So what we proved is that if the Kn converge to the square weave, then the limit of the volume densities is exactly equal to V oct, which we just saw is the volume density of the square weave. Right? So, and we call these geometrically maximal knots. And the reason for that is that you can always decompose a knot, or link in S3 into octahedra with one octahedron at each crossing. And you know that the volume of a hyperbolic octahedron is bounded by the hyperbolic volume of the regular ideal octahedron, right? And so you get the volume density is bounded by V oct. And then Colin Adams showed that this is actually a strict inequality. But so this is why we call these geometrically maximal, that the limit of the volume densities is V oct. What was surprising is that the determinant densities, right? So this is this quantity that we call the determinant density, 2 pi log det divided by the crossing number also converges to V oct. And so a natural question is, well, what is the toroidal invariant that's the limit for the determinant density? Right? So V oct is the geometric volume density. So what's the thing on the quantum side, on the diagrammatic side? So one way to think about this is in terms of the spanning trees, right? So the square weave has a take graph, which is given by the square grid, right? And so we saw the spanning tree entropy of the square grid, right? The spanning tree entropy of the square grid is V oct, right? And so this is enough to establish the result for the square weave. But we want to compute this quantity, this determinant density, this limit of determinant densities for any biperiodic alternating link. So we need a different tool. We need a kind of a different approach. So this is where the dimers come in. So a dimer covering is a set of edges that covers every vertex exactly once, a perfect matching. Okay? So the dimer model is the study of the set of dimer coverings. And so if Z of G is the number of dimer coverings, then Castellan showed in 1963 that if you have a balanced bipartite planar graph, that the number of dimers is given by the determinant of the Castellan matrix. Okay. So there's a connection between the dimers and the spanning trees, and it's a generalization of the temporally bijection. So you take a graph G, take the graph G star, overlay them, you get and then delete one vertex of G, one vertex of G star, and you get a balanced bipartite planar graph. And then a dimer on this GB exactly corresponds to a spanning tree on G. So there's a bijection, and this was discovered by Burton and Pimentel, explicitly generalizing Temperley's result, and then rediscovered by Propp, that the number of spanning trees and the number of dimers are related. So what we want to do is now do this in the biperiodic world, in the toroidal world. Okay, so here's the construction. We want to start with a biperiodic alternating link and produce a biperiodic bipartite overlaid graph, this GBL. So here's the construction. Start with the biperiodic link, pick a fundamental domain. So this was shaded on the computer, but I guess here it's not shaded. This guy's affecting the colors. Okay. So from the link, take the projection graph. There is a checkerboard coloring here. There is I promise you, a checkerboard coloring here. That checkerboard coloring corresponds to a tape graph. Okay. If you pick the other checkerboard coloring, trust me, it's different. Then that corresponds to a different tape graph. If you overlay the two tape graphs, right, this is the bipartite graph, then throw away the projection graph, you get a biperiodic overlaid graph. Okay? If you remember the fundamental domain, you get the toroidal overlaid graph. Okay? So that's the construction. Okay, from this we want to construct the Castellan matrix. So the Castellan matrix, so if you let again GB be a balanced bipartite toroidal graph, then the Castellan matrix is defined by three choices. Right? You have to make three choices. First, you have to choose signs on edges so that every face with 0 mod 4 edges has an odd number of signs. That's called a Castellan weighting. And it's a non-trivial theorem that every such graph, every bipartite toroidal graph admits such a Castellan weighting. This is kind of the heart of the theorem. This is a difficult point. Now you choose a meridian and longitude basis on the torus. And if we orient each edge from black to white, we can assign a weight for each edge using intersection numbers. And then we order the black and white vertices, and we get the black by white adjacency matrix with these signs and weights. Okay, so it's a lot of words. Here's an example. So here is a 2 by 2 example. So 2 black vertices, 2 white vertices. And this is the Castellan matrix. So let me explain why, for example, this is the first entry. So from the black vertex, there are 2 ways to get to this first white vertex. So one way is to just go straight across. That's this -1. And then one way is to go around. And this turns out, if you look at the intersection number, that's exactly a 1 over z. So that's a -1 over z because of that minus sign. From 1 to 2, there are also 2 ways to get here. One way is to go straight across. That's the +1. And one way is to go around. And that's the w, if you again do the intersection. So it's straightforward. This is easy to compute. Okay.
Is there a higher genus generalization?
So you want a dimer model on a thickened surface, on another surface. So this is, I believe the answer is yes, due to work of Kenyon. So Kenyon is the expert on dimer models. And I believe in a recent paper, this is new. If the answer is yes, and it's a couple years old. And I don't know how to do the Castellan matrix there. Okay, but I think, so there's definitely a dimer model on higher genus surfaces. Okay, so here is the setup now. We start with a GB is a biperiodic balanced bipartite planar graph, which is invariant by translations by lambda. Then the characteristic polynomial of this toroidal dimer model is the determinant. P of ZW is the determinant of the Castellan matrix. Okay? And so the theorem by Kenyon, Akunkov, and Sheffield, an Annals paper from 2006, is that if you take the toroidal exhaustion of GB, right, then the limit of the dimer entropies is given by the Mahler measure of the polynomial P of ZW. So the Mahler measure of the characteristic polynomial is giving you the dimer entropy, right? The limit of the number of dimers divided by the number of vertices in a toroidal exhaustion. And the point of the proof is that this limit does not depend on any of the choices we made to get the Castellan matrix. Okay.
Is the theorem about approximation of the Mahler measure by finite quotient subgroup?
I don't think so. I believe, I mean, the point is to express this as the correct Riemann sum for the Mahler measure.
Yes, yeah.
Is that what you said?
Right,
Yes. Yeah. It winds up being a Riemann sum argument at the end.
Right, yeah. Yeah, but I mean, in general, it's very difficult to control the singularities of the Mahler measure.
Yes.
Yeah,
That's
so
true.
this is just for some special cases because there's no general
Well, it's a
statement.
That's right. I mean, this is a toroidal exhaustion by n lattices, right? Am I answering the question?
Yeah, I mean, as I understand, there's no general statement about, I mean, if you can use the finite quotient to approximate the Riemann sum of the limit of the integral. But maybe there's some,
Okay, so their proof uses the fact that these P of ZWs are very special. They're Harnack curves.
Yeah.
They study the amoeba of these curves, and then they show that this limit is the Mahler measure using this algebraic geometry. So they're using some heavy-duty number theory. Okay. I don't think I'm answering your question though.
Yeah, maybe I answered it.
Okay. So we used their result. We did not. This is a direct application of this big tool. Okay. So here's the idea, right? So if you take a biperiodic alternating link with a toroidally alternating quotient link, L, then if P of ZW is the characteristic polynomial for the toroidal dimer model, then if Kn approaches L, converges to L in this Follner sense, right? Then the determinant densities converge to exactly this quantity, 2 pi times the Mahler measure of P of ZW divided by the number of crossings. And that turns out to be the toroidal quantity that is the limit that we care about. Okay? And so I want to discuss that quantity. The idea of the proof here is straightforward. This does not use heavy-duty number theory. The idea of this proof is that the spanning tree model on the take graph is basically equivalent to the toroidal dimer model on the biperiodic overlaid graph, right? That there's a limit of spanning tree entropies of planar exhaustions that's equal to the limit of dimer entropies of the toroidal exhaustions. Okay? Let me leave it at that. So let's put all this together for the square weave. All right, so here are all of the ingredients. We start with the biperiodic link. We pick a fundamental domain with 2 crossings. Okay? Therefore, the volume of T2 cross I minus W, minus this toroidal link, is 2V oct, right, by the theorem that gives us the hyperbolic structure. This is the overlaid graph for the square weave. And then, coincidentally, it's the example we just did a few slides ago. And so we know the Castellan weighting, and we know the Castellan matrix. So P of ZW is the determinant of that matrix. And this is the characteristic polynomial for the square weave. Now, 2 pi times the Mahler measure of this polynomial turns out to be exactly 2V oct, a small miracle. And that computation is due to David Boyd. I'll outline that computation in a while. But so as a consequence, the limit of the determinant densities, right? The limit of the determinant densities is equal to V oct, right? This quotient, which is exactly the volume density of the square weave. Okay. Here's the other link that we were looking at before. The triaxial link, we pick a fundamental domain now with 3 crossings. These are the overlaid graph. This is the biperiodic overlaid graph. This is the toroidal overlaid graph. We pick a Castellan weighting on the graph, make all of the other choices. Here is a meridian and longitude basis. Now the volume, because there's only one hexagon in that fundamental domain, is 10V tet, 10 times the volume of the regular ideal tetrahedron. And then from this Castellan weighting, we get a Castellan matrix, and this is the polynomial. So this is the characteristic polynomial of the toroidal dimer model for this graph. Then the similar computation by Boyd gives us that 2 pi times the Mahler measure is exactly 10 vtet again. And so in this example, the limit of the determinant densities is equal to 10 vtet over 3, because there are 3 crossings in the fundamental domain, which is the volume density of the triaxial link. The little miracle occurs again. So using the triaxial link, we can now find the spanning tree entropies for the other regular plane lattices. So for the regular triangular tiling, right, this will be this spanning tree entropy. And then there's a dual hexagonal tiling that has spanning trees there. So every fundamental domain that we saw has 3 crossings. Now we need to make an adjustment here, because of these 3, 2 are on hexagons and 1 is on the triangles. You can look back at the previous picture to check what I'm saying. And so 2 pi times the spanning tree entropy gives us exactly the quantity we were looking at before with this adjustment. We have to divide by 3. And so we get 2 pi times the Mahler measure of that P of ZW, which is 10 vtet. So that's the spanning tree entropy for the triangular lattice. And for the hexagonal lattice, the adjustment here is 2/3, and so we get 5 vtet. So once again, we're seeing a growth process where the number of spanning trees, this exponential growth rate, is given by a hyperbolic volume. This hyperbolic volume is different in this case. Okay, so let's look at another example, the rhomba trihexagonal link, the different biperiodic alternating link with the rhomba trihexagonal tiling. So this is the fundamental domain with 6 vertices. These are the overlaid graphs. Now, this fundamental domain has 1 hexagon and 3 squares, and therefore the volume is given by 10 vtet plus 3 v opt. So as a number, it's 21.14 something. Okay? The characteristic polynomial is this guy, and 2 pi times the Mahler measure is 10 vtet plus 2 pi log 6, an exact computation. That's 21.4 something. Now they don't agree. They're a little bit different. But the key point is the inequality. This one is a little bit bigger than that one. And so the determinant densities converge to something a little bit bigger than the volume density of the rhomba trihexagonal link. And this is a general phenomenon. Okay? So in a perfect world, we would like this conjecture, and this would be the tool that I'd want to use. So this is, if you have a biperiodic link with a toroidally alternating quotient link, L mod lambda, then for any hyperbolic links Kn that converge to L, it would be great if the volume densities converge to the volume density of the biperiodic link. We can't prove this. And the reason we can't prove this is we don't know the asymptotically correct lower volume bound. So we do know it for the square weave and the triaxial link for a fundamental reason. They're right-angled, right? And so the right-angled structure gives us asymptotically correct lower volume bounds. But in general, that's not going to be true, and so we can only prove it for 2 cases, this particular conjecture. But in these 2 cases, the determinant densities converge exactly to the volume density, which is the limit of the volume densities of these Kns that converge in this diagrammatic sense. So here is, for these 2 links, the limit of the determinant densities is equal to the limit of the volume densities. But that's not going to be true in general. So this is where you make lemons out of lemonade, right? Lemonade out of lemons. So if the Vol-Det conjecture, right, we know the Vol-Det conjecture is an inequality. So the idea is to use the biperiodic alternating links to obtain infinite families of links that satisfy the Vol-Det conjecture. Okay? And so this is possible if the limit of the volume densities is strictly less than the limit of the determinant densities. And so the idea is a 2-step argument. So step 1 is to prove using an exact Mahler measure computation that the volume of T2 cross I minus L is less than 2 pi times the Mahler measure. And the second step is to use the geometry of T2 cross I minus L to prove that if Kns converge to L, then the volumes, then we basically get the Vol-Det conjecture for almost all n. Okay? And for the rhombotrihexagonal link, we can do both steps. Okay? It turns out we can do step 2 in general. I will show you the proof in a moment. But step 1 is hard. And the reason step 1 is hard is this word exact. Okay, so I'll show you cases where we can do that too. Okay, so the tool we need is the bipyramid volume. So let Bn denote the hyperbolic regular ideal bipyramid, right, whose link polygons at the 2 coning vertices are regular n-gons. So for example, B4 is the regular ideal octahedron. Okay? The volume of such a bipyramid is known. This is the formula for it. And Colin Adams showed that the bipyramid volume is bounded below and asymptotically converges to 2 pi times log n over 2. Okay? So now, if you have a link in T2 cross I with a toroidally alternating diagram on T2 cross 0, then we define the bipyramid volume as the volume on the faces of the link. So this is a hyperbolic volume that's fundamentally a diagrammatic invariant, right? So this is a diagrammatic invariant that's obtained by geometrically putting a face-centered bipyramid on every face. Okay? And so what we proved is that the volume of T2 cross I minus L is always strictly less than or is less than or equal to the bipyramid volume. And this is a sharp bound for volume with equality for all semi-regular links. So for the semi-regular links, the bipyramid volume is the volume. Okay. Okay. So now, this is the conjecture 1 is that if you have a biperiodic link, then the bipyramid volume is less than or equal to 2 pi times the Mahler measure of the characteristic polynomial of the corresponding toroidal dimer model. Now, if that's true, then we know by our theorem that the volume is less than or equal to the bipyramid volume. Okay, so now, if this is a strict inequality, that's an if that's a strict inequality, then, so if the bipyramid volume is strictly less than 2 pi times that Mahler measure, then we get the Vol-Det conjecture for almost all n. And in fact, we get these infinite families, right, satisfying the Vol-Det conjecture of almost all n for every sequence that Follner converges to the biperiodic link. So you get many, many infinite families of this satisfying this Vol-Det conjecture. Okay. The proof hinges on proving that volume density convergence conjecture, which we don't know how to do, but we can do it for the bipyramid volume. So this is the bipyramid volume density convergence. And in this case, if Kn approaches L, then the limit of the bipyramid volume densities does converge to the bipyramid volume density of the toroidal link. Again, fundamentally because it's a diagrammatic thing. Now, the limit of the volume densities is less than the bipyramid volume densities, right? We proved that before. So that's now strictly less by hypothesis. So that's giving us this limit of the determinant densities. So the upshot is that the volume densities the limit of the volume densities is less than the limit of the determinant densities. And that gives this Vol-Det conjecture for almost all n. Okay, this proof fails if the limit of the volume densities is equal to the limit of the determinant densities. And that happens in the 2 examples that we know and love, the square weave and the triaxial link. And so this is now a numerical check. We just checked it by computer for hundreds of crossings that the Vol-Det conjecture does hold. Like here's a typical example. This is a weaving knot. So you take something that's basically a torus knot and you alternate it. And so you take this larger and larger gadget and we check that the Vol-Det conjecture holds. Okay, but that's not a proof. So here's a typical example. So I've been giving you these very special examples. Here's a kind of generic example. So this is not semi-regular. It's just something. And it has, in a fundamental domain, it has 1 octagon, 4 pentagons, 1 square, and 8 triangles. Okay? So here's a very nice biperiodic link with nothing special that I can see. And so the volume is 47.6 something. the bipyramid volume with these faces is 47.7 something, right? Our theorem said one's always going to be bigger than the other. The characteristic polynomial for the corresponding toroidal dimer model is this mess. That's hard to compute the Mahler measure. That's a genus 8 polynomial. Numerically, it's 47.9 something. And so that conjecture 1 that we saw is satisfied within a range of 0.6%. Very close, right? So the volume is less than strictly less than the bipyramid volume, and it's strictly less than 2 pi times the Mahler measure of the characteristic polynomial. For any such example, the Vol-Det conjecture holds for all but finitely many knots. Okay, when can we compute, or how do we compute the exact Mahler measure? So let me talk a little bit about that. The idea is the following. So this is an argument that, again, goes back to David Boyd. The idea is a trick. You think of the polynomial p of xy as a polynomial in x where the coefficients are algebraic functions yj of x. So you kind of treat it as a one-variable polynomial, and then apply Jensen's formula, and you get this sum of integrals with eta of x, yj. That eta is quite special. That eta is this gadget here, which is a closed differential form called the volume form. Okay? It's related to the Bloch-Wigner dilogarithm, d of z. Now, that dilogarithm is defined using the classical dilogarithm. The important point is that on the unit circle, it's given by the values of the Lobachevsky function. It satisfies the 5-term relations, and therefore d of z is the volume of the hyperbolic tetrahedron with shape parameter z. And the derivative of this Bloch-Wigner dilogarithm is eta of z 1 minus z. So here is the game. If eta of xy can be expressed in terms of these z 1 minus z's, then we can use Stokes' theorem and evaluate the Mahler measure of p of xy exactly in terms of the Bloch-Wigner dilogarithm d of z and get these hyperbolic volumes. Okay, so take the zero locus of the polynomial, and now if we can write x wedge y as a sum of z wedge 1 minus z's, then eta of xy can be written as a sum of these eta z 1 minus z's, which is d, the derivative of the Bloch-Wigner dilogarithm at those z's. Therefore, integrating the Mahler measure of p of xy is just some sum of these alpha times these Bloch-Wigner guys on some boundary condition, right? Now, a priori, we may not be able to solve this condition star. That's the difficult step. So we can always do it for the A polynomial of a one-cusp hyperbolic manifold. And if the curve has genus 0, then we can solve this condition star by parametrizing the curve. Okay? So let me show you the Boyd's computation for this example, for the example that we care about for the square weave polynomial. So the step 1 is to start with this polynomial, this two-variable polynomial, and factor it in a clever way. So this is the clever factorization. The logarithmic Mahler measure is additive on these polynomials. So it's twice the Mahler measure of this fellow. Okay? Now, the zero locus lets us then parameterize, I'm sorry, got cut off. Z is then can be expressed in terms of these W's. So W wedge Z, which is this condition star that we care about, can be written as a sum of two fellows. This is Z wedge 1 minus Z, and this is a Z wedge 1 minus Z. Okay? So, on the unit circle, if we parameterize W on the unit circle, then Z is going to be outside the unit circle only for these thetas. So we get the boundary condition, W is between -1 and 1. So then, the Mahler measure of P of ZW is the sum of these Bloch-Wigner dilogarithms on this boundary, and when you evaluate it, you get exactly a sum of these D's. You plug it in for this boundary condition, and you get 8 times D of I, and that, by the Lobachevsky function, is exactly 2V oct, an exact computation. Okay? Okay, So we used Boyd's computation to prove this conjecture for the three examples that I discussed, right? So the square weave, the triaxial, and the rhombotrihexagonal. And then we used other exact Mahler measure computations, basically same idea with more complicated polynomials, more complicated steps, but the same basic concept with the volume form, to prove it for three other examples. Let me show you this last one. Here, this is the characteristic polynomial for the dimer model on this guy. It turns out that 2 pi times the Mahler measure is exactly this quantity, which I'm just showing off some digits here, 19.7 something. The bipyramid volume for this link is 19.6 something, and the actual hyperbolic volume is 19.5 something. So this link satisfies conjecture 1 and this inequality within a range of 0.4%. This seems kind of the generic thing that's happening. And again, for this example, because this is now a rigorous proof, we get the Vol-Det conjecture for all but finitely many n. Okay, finally, what I want to do is try to suggest a reason why 2 pi keeps appearing everywhere in my talk, right? So a tower of covers is given by, right, a sequence of finite covers. So for a hyperbolic, for any three-manifold, the first homology can have arbitrarily large torsion subgroups. Now, a conjecture due to Tang Lei and some other people is that for a closed or a one-cusped hyperbolic three-manifold, in this tower of covers, if the fundamental groups are cofinal, then the limit of this exponential growth rate of the torsion of the first homology divided by the volume of these MNs is equal exactly to 1 over 6 pi. And this is a special case of Wolfgang Luch's approximation conjecture in L2 torsion theory. And so for a closed hyperbolic three-manifold, the analytic L2 torsion of the covering transformations of H3 is exactly minus 1 over 6 pi times the volume. That's where that 6 pi comes in.
So, but are these covering regular?
Yeah, these are. So I think so. If you have the cofinal condition, that you get that from the regular covers, doesn't imply the regular covers.
So these coverings are they regular coverings?
My cover, I will talk. Yes, they can be regular coverings. Is this true for? Is this conjectured for non-regular coverings?
There's conjecture for non-coverings.
If you satisfy this condition. I thought you don't need regular covers as long as you have cofinal. But I would ask you. All right. So now let's return to the determinant, right? The determinant we saw is the order of the homology of the twofold branch cover. It is also, therefore, the order of the torsion of the twofold cyclic cover of the knot complement. So now what we want to do is do the toroidal variant of this. So let X of L be the twofold cyclic cover of T2 cross I minus L. And that's given by the kernel of the fundamental group of T2 cross I minus L to Z mod 2, where the L meridians go to 1 and the Hopf-Link meridians go to 0. And so what we proved is that if you have any hyperbolic biperiodic alternating link, if you take an exhaustive sequence of toroidal quotients by NZ cross NZ, then for the characteristic polynomial for the first one of those, the fundamental domain, L1, then the limit, right, of the exponential growth rate of the homological torsion divided by the growth rate of the volume for these X of Ln's is given exactly by the Mahler measure of P of ZW divided by twice the volume of T2 cross I minus L1. Now, if you take a subsequence, then you actually get a tower of covers. This is a sequence of covers. Here you get a tower of covers with exactly the same limit. So these X of Ln's all cover X of L1, and then for the subsequence, they cover each other. So now, since you have a common cover, X of the biperiodic link, they all have a common cover, you are very far from cofinal. So this is not a case of the conjecture that I had before on the previous screen. But so this brings me to the third example of this growth process and hyperbolic volume, right? So now, if you take the square weave or the triaxial link and take these toroidal links, these toroidal exhaustions, where you have 4 n squared crossings in the square weave case and 3 n squared crossings in the triaxial link case, then what we showed is that the exponential growth rate of the torsion of the first homology divided by the volume of Wn's and of the Qn's for both is 1 over 4 pi, exactly. And as far as we know, these are the first examples of non-cyclic towers of covers of hyperbolic 3 manifolds whose exponential homological torsion growth can be computed exactly in terms of volume growth. Okay? And the question that I don't know is, can this 1 over 4 pi be explained in terms of the L2 torsion of the covering transformations of these biperiodic links? And I think this is what Tan was asking me at the beginning of the talk. Is it related to the L2 torsion theory here? And this is where I think it would come in, where the L2 torsion theory would come in. Okay, so what happens more generally, right? So we have a theorem here for any of these biperiodic links, right, and these toroidal exhaustions. We have this conjecture that the volume of T2 cross I minus L is less than 2 pi times the Mahler measure of the characteristic polynomial. If we put these two together, then together they imply that for any hyperbolic biperiodic alternating link, the log, right, this exponential homological torsion growth divided by the volume growth of x of Ln is going to be greater than or equal to 1 over 4 pi. And the equality is for the square weave and the triaxial link, which we proved. But this conjecture would imply that this is always greater than or equal to. So for the rhombotrihexagonal link, which we know exactly, right, we have an exact Mahler measure computation for it, this limit of this homological torsion growth divided by the volume growth is 1.01 something over 4 pi. And for the others that we computed the Mahler measure exactly, we get similarly just a little tiny bit above 1 over 4 pi. Okay. So thank you very much.
Technical. Is there any chance you could put your slides on the web somewhere?
They are on the web. They're just yes. There. Do you want me to
how do I find it? Sorry, I mean.
No, that's fine. Yes, I'll. Sure.
Type a random URL. It will not.
Yeah. So, should I write a URL on this piece of paper? It's long. It'll be long. Should I?
Well, or tell us how to find it. What should I type in?
Okay.
Go to your homepage.
Yeah, I will make the link public. How's that? But right now it's a private link. So if you Google my name, it will be up there and by today.
Okay.
Just Google my name.
Yes. Okay. Thank you.
Sure.
So, you have questions?
Yeah, I have a question. Last comment. Stephen Barton also showed the following: like, if you were to order your links, organize them or alternating links in terms of twist number instead of crossing number, then for every twist number, there is at most finitely many nodes, links that will fail in Vol-Det Conjecture. Have you tried to, and then you have all this nice, great computation of things. Have you tried to combine the two and see?
No. So that would be very interesting. So I have tried to disprove this conjecture in many different ways. I did not believe this conjecture at first. So I'm like, how could this be true? So this is anyway. I'm more convinced of it because of failures to disprove it. So Right, so this would be, if you have other ways to try to disprove it, that would be
Okay.
interesting.
Not disprove.
Yeah, I see.
Whatever.
Yeah.
Go on.
Like, for example, if you take an alternating link, so it implies the following thing. If you take any alternating link and augment it. So Thurston's Dane surgery theorem tells us that the volume will go up, right? And so the Vol-Det conjecture implies that that volume will always be trapped between the volume of the link and the volume of, and 2 pi log determinant. So any augmentation around 2 strands for an alternating link. They kept trying, I've tried many ways to try to do that. And it's always in the middle. So.
Okay, any more questions, comments? If not, let's thank. Cool.